Uh, Hello, everybody. Please take a seat. We'll be starting. All right. Thank you very much for coming to my presentation. It's Atomic Habits in Writing High-Performing Distributed Code in the Cloud. Before we start, does any one of you know what atomic habits are? Please raise your hand. 1, 2, 3, 4, 5 people, 6. Thank you. Maybe a couple of words about me. I'm Bartosz Wieczorek, Senior Principal Software Architect at Sabre. So this is the small planet where I work for. And I'm helping teams within Sabre to write high-performing code, especially considering the cost in the cloud. I'm responsible for cloud architecture, and I'm a conference speaker, and you can see some pointers to my blogs, repo with code examples, even including from that presentation. So if you have some questions, also you can contact me there. What is Sabre? Sabre is a software company that builds solution for travel industry, and it's located in Kraków, and also in headquarters in US, and also a quarter in Bangalore, in India. So the agenda for today is what are the atomic habits? A more systematic approach to performance optimization and cost reduction in the cloud. And I'll be also presenting a real case code examples, how we were able to increase the performance and optimize the cost. So what are the atomic habits? The term comes from the book by James Clear. Imagine a story described in that book that the group of cyclists in Great Britain are performing so poorly that the bike manufacturer who is renting them the bike equipment doesn't want to do that anymore because that manufacturer is afraid of getting negative associations, so no one would buy bikes from that manufacturer. But luckily for the team got a new trainer with a revolutionary technique that is called atomic habits. And what are these atomic habits? These are essentially like small changes introduced on a daily basis that in a long term help you to improve. And in their example, after applying like very simple changes to the training, such as like making sure they eat better food, making sure that they have a regenerating sleep, that they use the right gel for muscle regenerator, or they use better sports clothes to make the muscle temperature more stable. With that systematic approaches, they were able, after 6 years of applying them on a daily basis, they were able to win 60% of Olympic medals in Beijing in 2008, and 4 years later in the Olympic Games in London, they set 9 Olympic records and set 8 world records. So that could be an inspiration, that story, not only for the code and the way you work, but also for yourself in your private life. For example, I don't know, eat more healthy food or organic food, or take a walk after work. Small little things that doesn't take much time, but maybe it will, after some times, you will realize that it can significantly change your life. But getting back to the use case, After applying one of the principles, at the end of the presentation I have them all listed. These are 16 principles. But one of these principles that I applied and I'll be talking to about help us to reduce the pipeline cost, so the data flow job pipelines, by 45%. And we will be talking about the scenario where we process like terabytes of data every half an hour. And that was just the case for a single project, a single pipeline. So we scaled it out and we save a lot of money. So this is the use case. This is really the our case. A little bit because how we got to these high numbers, and that specific job or a processing pipeline every 30 minutes is ingesting, so processing 300 GB of data, and at peak even 600 GB of data. And it's to process that amount of data, it uses the auto-scaling, so the number of machine that is used to process the data in the peak, it's 100 nodes, and it can scale down during the night if not so much of the volume is being processed. And in our analytical data storage, which is BigQuery, we are on GCP at Sabre. We have 12 petabytes of logical bytes of data and 127 billion of records in that specific one table for the project we did the optimization. We are getting the data from the Google PubSub, which is like queue, and sometimes we process the data also from Google Cloud Storage, which is like a remote persistent storage. Speaking about the systematic approach to performance and cost, we need to set our targets, goals, and alerts, how we want to address them. So if you're optimizing something, it's important to look around if there are low-hanging fruits that can give you quick saving. On the other hand, you don't want to spend like months or years of time just to optimize maybe 1 or 2%. So it's important to set these goals, and if you're ingesting the data in the real-time manner, it's important. One of the objectives is to set data freshness. Okay, what it means is that when you get the data into your storage, into the BigQuery, how long did you need to wait since that it was emitted from the source up till it ended up in the destination. For the batch job that it's processing like hundreds of files from the GCS, Google Cloud Storage, what is your target? How much can you wait until the job finishes processing all the data? And how much of the money can you spend on processing the data? Because that also influences decision whether you will be doing that once a day, once an hour, maybe every 10 minutes, or in real time. These can be also conflicting with each other. So set the alerts, set some dashboards where you monitor the cost. So you know what you're optimizing for, and you have immediate feedback loop. What I will be describing here today are three main topics. First is the framework that we use for processing lots of data. Extract, transform, load is the framework that is the concept that in general takes a lot of data, makes the transformation of the records, parsing, filtering, aggregating, and loading to the final storage. And we were able, as I mentioned, to do the 45% of a cost reduction. The second use case is when we change how we deliver the records or the data to our processing pipeline. After we changed that, we were able to process the data 4 times faster. In other words, the really old solution, we were not able to go above 80 transactions or 80 elements per second, because these were fat, really big elements that it was really hard to parallelize, so achieve fast throughput. But after changing that, I will describe that we were able to go 4 times faster. So with these small messages, we can achieve easily tens of thousands of transactions per second. I will describe that later, of course, in the presentation. And the last piece of focus for today, it will be user code and pipeline flow optimization, because it also impacted in various ways how we optimize our processing. So what was maybe if you take one feedback from this presentation, if you're in the cloud and you're working on a virtual machine, the one thing to remember is revisit which machine you are using, which type of machine family you are using, because it can give you immediate saving of 45%. And that was the case in our situation. So, but what is the systematic approach to find the best performing machine? So maybe if you look into the documentation for Google, you will see like 10, maybe 20 of machine families. So which one to choose? Shall we go for the E2 standard machine, which is like a Dacia type? Not offend any Dacia guys. Bigster and Duster that have really high sales right now. So E2 standard 8 machine is a day-to-day computing at low cost. This is what Google says. So let's put it in one category. Then the regular machine for, let's say, best performance per dollar cost for scale-out workloads. And we are scaling out sometimes if there is high traffic. Let's put it Toyota there. And how about choosing, like, I mean, if we want to do it fast, how about going for speed cars? Let's go for BMW. So is it obvious that BMW will be the winner? So let's have a look into how we were able to find the best machine for our use case. So there are two factors to consider when choosing the best machine. First, which is like really the obvious one, it's the VM instance pricing. So how much would you pay for 1 hour of usage such a machine? That's really probably easy, straightforward thinking. But the second thing, important information is the core mark score. So how good is the machine? So if we glue these both of the information together, we can say that, okay, this BMW machine is really the most expensive one. Is it? Actually not. The most expensive one is the E2 standard A machine compared to C2D standard 8 machine, which was a surprise for me. And the another thing was that the score mark of the machine. So how much time do we need to spend to accomplish the same task? So you can see that for E2 standard A machine, it took like 100% of the time, and then BMW was able to complete that much faster, 33% faster than the E2 standard 8 machine. So does it mean that still BMW is the winner? Let's kind of multiply these two factors together, and let's see which machine is the best, offering the best performance per dollar. And actually the winner is the T2D standard 4 machine. The BMW C2D standard was close, but as this article says from Google, it's offering the best performance per dollar, these tau machines. So I really encourage you to have a look into the score marks and the pricing and run some tests. And you can save a lot of money just by simply changing the machine type. So that was easy. Now getting a little bit into big data processing, distributed processing. So this is our data that we want to process as an analogy. Look at this port here. There are many cargo ships. And try to imagine that one cargo ship is your machine, your node. So you see 3 cargo ships, 3 nodes. And then you can see many cranes that are putting these containers onto the machine. So think of that Java virtual machine running many threads, Java threads, on that node to do the work. So there are many cranes that are putting the containers, and maybe there is like a rear part of the container, and the middle one, and the front one. So essentially, these containers are maybe grouped into some areas, which I call them bundles. So this is one bundle of a container, this is the second bundle, and a third bundle of the container. And actually, each bundle will have inside I don't know, some goods that you want to transfer, let's say cars or whatever you want. And that really applies to the data flow framework that we use for big data processing with workers as cargo ships, GVM threads as cranes, and bundle of records, so bundle of goods that you want to transfer. And if you use this analogy here, you can a little bit have a look how it's being processed internally and why it's important. Why am I showing this to you? And why did I need to spend like 2 hours to prepare just for this presentation, this slide? It's important to remember that, okay, we've got 2 workers. This is the first worker, so first cargo ship. This is the second worker. It has a GVM. It has the first thread that it's processing the data, and a second thread, again, first thread and a second thread. These are containers, so bundles, and inside you've got your goods that you want to process. So it's important to know that these goods are not processed like the thread picks the good and then process it, but these are processed in bundles. It's important because if something fails, it's easy to reprocess a bundle because on the other hand, you want to checkpoint the data. So if something goes wrong, another thread or another GVM can resume the processing so your data is not lost. So, and what's important, and it's about point number 2, how your input data looks like. Here I'm showing you the Parquet file, which consists of multiple blocks inside the file, which is block 1, 2, and n. And what is important, each block of the file can be processed in parallel by different threads in different bundles, and that it can be up to 200 or 300 threads running on a single worker VM that is processing the data. So it's highly parallelizable. And why am I presenting that? Because really the speed up of the throughput we achieved by changing our source of sending us one gigantic zip file with 100 or 200 concatenate very huge nested XMLs, which we can see that was being, imagine the scenario that you receive such a gigantic XML or gzipped one, and you have 2 nodes to process the data. And apparently, it will be only a single thread unzipping the file and sequentially processing one XML after another. And that's very CPU and memory-intensive operation. So what's happened to another threads? This thread is idle. This worker is doing nothing. And in data flow world, we pay for the machines. So we want to utilize them as much as we can. The more we utilize them, the better we utilize them, the fewer machines we can have, so the cost is lower, but we can have higher throughput in one of the machine. So we redesigned the source, and they were sending us one XML inside one gzip. And some people after presentations can tell me or come to me and say maybe, but in that previous example we saved on a network. But yes, that's really true. But in that case, we were able much better to utilize the throughput because that XML was processed here, and by that thread, another XML by that thread. And imagine you've got 100 workers, and each worker can have 100 threads. So imagine how parallelly we can process the data if we receive 10,000 of such XMLs per second. So that gave us 4 times higher throughput and a lot of saving in terms of number of workers. The third optimization is about user code and the pipeline flow. So the code that the data flow is running consists of the data flow SDK code, which is written by the creators of the Apache Beam and Dataflow, but it gives us a hook so we can write our own processing code. So in a process method, we get in the input like a key value pair of string and bytes. Let's call it XML gzip bytes here, and we do some processing on that input key value, and at the end we want to output the result of our processing. That's why we have this output receiver here. So it's important to have this user code as much optimized as possible, because imagine that code is being executed 10,000 times per second across different nodes and JVM threads. So what are the ways of systematic measuring the application performance? Maybe you know that already. Use, sorry, it should be Java, benchmark harness. In my case, I needed to parse JSON. And I didn't know which library should I use. Should I use this library or that? There are many JSON parsing libraries here. And once I chosen one, which will really be the best one? Should I parse the string, or should I use the method parse string buffer? And once I annotate in my laptop one class with the right annotation from JMH, I was able to say that, okay, I can do much faster, like 3 times faster operations per second using parse string builder and achieve much higher throughput. So if I want to optimize my code, I can even do it on my laptop and then apply it to the large-scale data volume processing. So that was inside, that can be applied for any code, Java code in any projects that you're using. Another use case that we had a pipeline running in production, and it was processing lots of data, like lots of orders. And for every order, we wrote a custom loading to check if that order that we process is being restricted. So we needed to do the lookup. And the team who wrote that code initially wrote the put all the restricted order IDs into this list, and that was working pretty well. And up to the moment when there were like 2,000 of orders that should be checked in that list. that at least contain 2,000 orders. But after full production refresh, the number of orders became millions, and this contains lookup started to slow down the pipeline 2 times. So in order to keep up with production load, we were needed to span not 50 workers, but 100 workers suddenly, because we were not able to meet our SLAs. So in the running data flow job, you can turn on the profiler flag, which will tell you where are you spending most of your time. And I would expect to see that my business CPU intensive operation would spend, this is where the code will be spending most of the time. But apparently it wasn't, because if you look here, that random was only taking this piece. And the remaining, or the majority, maybe more than 90%, it was spending in the contains method. So just simply rewriting the restricted order list to the hash set or a hash map, it helps us to resolve the really academical problem of the time complexity big O of n versus big O of 1. So I really sometimes also encourage you to have a look for these algorithmical cases as well, to speed up your pipelines. Now we are getting a little bit more into big data. So what data flow is, what Apache Beam is, it allows us to process like lots of data. Each individual shape and color are different kinds of data in a batch manner. So you have all the data sitting in one place, ready to be processed. It's not changing, nothing new is being added. That's the batch approach. Or a stream of data, like a stream of tweets. And in Apache Beam and data flow, you can process them in using the same code. You just set the flag, okay, this is the streaming or this is the batch. In the same fashion. It's a unified processing model. So what can you do with the data? It's not only just a simple example as sending the cargo ship from one place to another, but you want to do some analytical operations there. So you want to filter out, have a look here. I'm filtering out all the shapes that are not squares. I can do the grouping. So let's say these are the squares, let's say where they are manufactured in different countries. So let's say orange is one country, red is another country. So you want to, at the end of the day, create statistics. Okay, what are the statistics for each country of the data that you want to process? Or alternatively, especially for the streaming pipelines, what you wanted to do, okay, you are not interested in like, you really want to specify your time boundaries, how often you want to recalculate your aggregation. Do you want to do that on a daily basis? So after a stream of, so every day, you will be calculating, okay, statistics about countries. So your window is 1 day, or you apply a window of 1 hour, or even a couple of minutes. So it's capable of grouping and windowing in a really powerful way. And why am I showing this to you? Because it's kind of helped me to detect one of the problems typical to the big data. Problems that was slowing down our pipeline. So don't worry about this. I will really explain what this is. So these are the, let's say, the goods that you are transferring or the data you are processing, coming from, let's say, different countries, from different organizations, which are represented by different colors. So you have a stream of data, and they may end up being processed in parallel, and the parallelism here is 4. So you have like 4 threads, even though coming from different workers. You can process them in parallel, and you can see different goods from the same countries are spread on a different nodes, on a different workers. And if you want to do the group by, which is really like the word in big data processing, really something interesting happens. What really happens there is that the same color, so the same key, the data for the same key needs to be on the same worker after grouping by. So all the red guys from the lower data flow, from the data flow 2, worker data flow worker 2 needs to go to the data flow worker 1, and on the opposite, for example, the yellow one needs to go from first worker to the second worker. So you eventually end up with the same color being only on the same worker. And this involves shuffling of the data. And when I had a conversation about different big data vendors, architects, how they are doing data shuffling, I mean, I was talking with Google data flow experts, I was talking with Spark experts. They use different techniques. For example, in data flow, they use SSDs, where all this data is being checkpointed and persisted to the local persistent disk, which is running next to the compute engine, and the state from one SSD is being transferred to another SSD. Another approach that is used in data flow streaming engine is that the state is not stored on the SSD, but the state is being sent to the specialized backend system, shuffle backend, and that backend is being used to shuffle the data. So with that approach, you don't need to have big SSD disks, because backend does it for you, but it comes with additional cost. If you want to use SSD, that may be cheaper, but it requires lots of testing to make sure that you don't end up with too small SSDs, because that would cause the read-write problem, or not too big SSDs, because you would pay too much for the SSD. So that's why in the streaming engine, there is no such concept of a big SSD, because the backend would do that. In Apache Spark, what they told me that how they solve that problem is they are able to automatically increase specifically the disk size to fit all the data. So why that piece is important? Because sometimes developers come to me and they say, okay, we applied all the previous techniques, but still our pipeline is slow. So what could be the problem? So imagine the case that your data distribution is looks like this in this picture. Let's say you've got much more green records. You've got a little bit of orange, pink or red, and you've got very few blue ones. And once you do the group by color, you will see that the one, and this is really the use case that I'll be presenting you based on the real code, you may end up with one data flow worker that is processing only that little of amount of data, and it's not being fully utilized to the full capacity, whereas the other one is sweating and it's blocking the pipelines to go faster. And in that case, now I'm able to show you the code for such a scenario. So our real use case scenario at Sabre is that we receive these XMLs. These are fat nested these are nested XMLs, so really big XMLs. These are gzipped ones. So I'm generating those XMLs at the rate of 40,000 of elements per second in parallel. and apply some windowing. So I'm interested in aggregation statistics every 10 seconds, sorry. And I'm doing a group by key here. So, you know, all the grouping records are being shuffled across the workers. So the same key is on the same worker, which I showed you before. And at the end of the day, what I want to do after this grouping, I want to ungzip that XML, parse the XML, maybe to extract some salary-related monetary number, and sum that values that belong to the same key, and log that to the screen. I could write it to the file, doesn't really matter. So how does it look like in data flow? We've got a block which represents our source of generating the data, windowing, then grouping, then unzipping, parsing, and really writing or to the screen logging in the sink. But what's important here, this group by keys breaks the fusion. What it really means is that this step and that step are being executed on the same thread. It just they share the result of the first operation in memory, and the same thread is able to fetch it from memory and do that windowing. So here is like what one thread can do. But here, after data group by key, there is new portion and a new group of threads that are being processing what comes after grouping. So these are two stages, stage 1 and stage 2, and they are split by the group by key. So how fast am I doing? So let's look at the data flow statistics. I'm starting with one worker, which is in the auto scaling. So I'm running one node. And since I want to generate the data at 40,000 of elements per second, it's scaling up because it's determining that the number of records to be processed is growing up, it's piling up. So the number of seconds to process all these records is increasing. And the CPU is high, so it's increasing number of raw workers from 1 to 3. But still it doesn't help because I'm running more or less like 10 thousands of, I'm processing the elements at the speed of 10 thousands of elements per second. Can I go faster? So let's have a look at the CPU utilization. So what's really happening here is that first I have one thread started, one node started, and that node, it's trying to do its best, like at 60–70%. Then other two nodes are starting. But you can see that this node is pretty much doing what it should do, maybe 70%. So it's good. But the other nodes are really not doing much. So to demonstrate that, I added the counters to demonstrate what's really happening here. And since I don't have much time, I can tell you that the key of the most distributed key, so 7 out of 10, which the US manufactured good, will be processed in that node. And also PL, let's say 2 out of 10 goods, is also being processed here. But Malta processed good, which is 1 out of 10, is being processed on that almost idle node. So that's not really fast way of processing. So how can we speed that up? Let's kind of once again remember, these are around, our throughput is 10,000 elements per second. Can we go faster? This is really the question. So what can we do? We can redistribute the key. So the country that's being manufactured. And how to do that? Just apply some random value to the key, append it. Before we do the group by key, then do the parsing, and then which is really heavy CPU memory intensive operation, and then remove that suffix from the key and do the combine per key. Adding the combine per key adds additional stage, but since we have already all the data on the same worker that it's supposed to be, it's pretty fast. And also, the heavy CPU intensive operation is already completed, so that should give us much higher throughput. So let's look right now how is the performance. So we were able to increase the throughput from 10,000 to 35,000, and you can see 2 out of 3 VMs are now running almost 100% CPU. What about the last one? Can we get to the stage where all of 3 machines will be running full capacity? And the answer is yes, we can. It's just as simple. It's not always the case that we can do it, but if we just move up the CPU intensive operation, which is unzipping parsing, from the place where it was below group by key, can we move it up and do that upfront, and then do the group by key and combine by key, or as a one-liner combine per key and a sum of longs? If we do that, we will still have 3 stages, because group by key adds 1 and combine per key combine grouped values introduce the stage, but really the performance will be not 10, not 25, but will be 35, and we will use full capacity of the workers. And we don't need to do any key manipulation. So that's important to have a look in your pipelines if you can uplift your CPU intensive operation, if that is accumulative, like summing, in the combine per key up before really the group by key. And if you do so, you can improve the performance. I think the agenda could have been much bigger to do the daily optimization, to do the daily improvements. But I wanted to highlight you what was the most interesting thing for me in my daily work. Sometimes you can, I'll be sharing the slides. Sometimes you can read out of them and find maybe it may not trivial, but let's go for Java because it's much faster than Go, and Python for data flow, it's 30% slower. This is what even Google says on their conferences. And there were some other guys coming to me saying that they were written from Python to Java. Maybe you don't need to go with the streaming approach because the VM is much more expensive there, VM compute cost, than if you use the batch pipelines. And there are more of them that you can have a look. I couldn't cover that all. And if you're interested in any of these items that I listed there, I described them in previous my conferences. Here it was just the latest troubleshooting I discovered, which impacted my performance of the application. So thank you very much. I hope you will find it useful, and let me know if you have any questions.